As part of a continuing program on aviation safety, the Lewis Flight Propulsion Laboratory of the National Advisory Committee for Aeronautics has been engaged in research on the start of fires that sometimes follow airplane crashes. The work was undertaken at the recommendation of the NACA Committee on Operating Problems and the Subcommittee on Aircraft Fire Prevention. These groups are made up of leading representatives of civil and military aviation. It was the purpose of this research to provide a better understanding of the important factors involved in the start and spread of crash fires as a necessary first step leading to significant reduction in the crash fire hazard. The work reported in this film covers only the research completed on airplanes powered with reciprocating engines. A thorough review of civil and military crash fire records emphasized the need for well-defined information on how crash fires start. This review showed this information can only be provided by full-scale crash studies. Findings of this study were published in an NACA research memorandum entitled Analysis of Multi-Engine Transport Airplane Fire Records. With the need for a full-scale crash fire program established, the United States Air Force provided a group of service-weary aircraft marked for decommission with which to conduct the research. A landing or takeoff accident was chosen for study because the chance for passenger survival of crash impact is highest in this type of crash, which occurs at reduced airplane speed. The airplanes were carefully instrumented to collect detailed information during the crash. 72 vapor detectors located in the engine nacelle, wings, and fuselage registered the presence of combustible vapors. Over 100 flame detectors similarly located recorded the origin and spread of fire throughout the aircraft structure. All the main electrical circuits were monitored at the locations shown on this chart to indicate the presence of short circuits. Instrumentation was also provided to indicate the time at which fuel lines ruptured in a crash. Such detailed information is registered on this instrument panel inside a fireproof box carried in the airplane. The instrument panel is photographed by motion picture cameras within the box. In a crash operation, the airplane is accelerated from rest under full power and is guided into a crash barrier by a slipper in sliding contact with a rail. This barrier is composed of an abutment in the path of each landing gear wheel. The abutments strip the landing gear from the airplane. The propellers strike the abutment at full engine power to produce extensive damage to the engine nacelle. The pair of poles on each side of the abutment cut into the wing fuel tanks, causing spillage of the fuel. At the moment of crash impact, the airplane is moving at about 90 miles an hour. The airplane carries 1,000 gallons of fuel in the tanks outboard of the nacelles. The fuel is sometimes dyed red for photographic purposes. A detailed description of the method of conducting these crashes was published in the NACA research memorandum entitled Facilities and Methods Used in Full-Scale Airplane Crash Fire Investigation. To understand how crash fires begin, it is necessary to learn where and when ignition sources exist and how the combustibles move from the spillage zones to the ignition sources while these sources are still potent. Many ignition sources are carried on the airplane, others are generated in the crash area. A large number of ignition sources are located in the engine nacelle, which contains the engine and hot metal parts of the exhaust system. Flames appear at the engine intake in the familiar backfire. Likewise, flames appear at the exhaust outlet. The electrical system of the airplane represents the most widely distributed ignition source. It extends from the nacelles into the wings to power fuel pumps and lights, into the fuselage for lights, navigational instruments, and airplane controls. Of the combustibles carried in an airplane, only those in liquid form are likely to contact ignition sources in a crash. These combustibles are fuel, hydraulic fluid, lubricating oil, and alcohol. The crash fire threatens human survival only when the fuel becomes involved in the fire because the other combustibles are present in small quantities. However, the other liquid combustibles may be the first to ignite and in turn set fire to the fuel. In the conventional airplane, most of the fuel is stored in wing tanks. The tanks are interconnected by pipes so that fuel from any tank can serve all the engines through main lines which run to the engine carburetor. In a crash, fuel often is spilled in liquid form from broken fuel lines. Likewise, liquid spillage occurs from damaged tanks. Pre-mixed fuel vapor and air spills from the damaged engine induction system, and a combustible fuel mist sometimes forms around the airplane. The airplanes were crashed in ways that resulted in all these forms of fuel spillage. In studying how the fires are started, it is necessary to consider the ignition sources along with the fuel spillage. The following discussion will take up the various forms of fuel spillage and how the fuel moves to the ignition sources. The characteristics of the ignition sources will be discussed at the same time. Because the fuel in the mist form played such an important role in the crash fires experienced in this study, fires involving fuel mist will be discussed first. When the liquid fuel spills into the open air while the airplane is in motion, it is atomized into a mist. In this scene, shown at 1/5 normal speed, watch how the fuel, dyed red for visual clarity, develops into mist during a crash. As the fuel pours from the tanks, breached by the poles at the barrier, the fuel is atomized to mist, a part of which remains suspended in the air. The plume of the fuel mist streams directly rearward from the break in the tanks if the damage to the airplane in the crash results in only moderate deceleration and the airplane continues forward at high speed. When the airplane moves at low speed with high deceleration, the fuel surges forward out of the break in the tank. This results in a broad fuel mist pattern in the forward portions of the airplane. Under such conditions, contact between fuel and ignition sources at the nacelle is likely. Now watch in the next crash the transition of the fuel mist development from the high-speed, low deceleration pattern to the low-speed, high deceleration pattern. Here comes the airplane at about 90 miles an hour. The motion is reduced to 1/5 normal speed. Impact at the barrier will produce momentary moderate airplane deceleration. Observe that the fuel, dyed red, streams directly back from the leading edge. When the airplane strikes the ground with high deceleration, the fuel mist develops well forward of the wing leading edge and spreads span-wise as the airplane slows. In view of these effects, the fuel mist can be expected to contact an ignition source which lies span-wise from the point of fuel spillage as the airplane slows down. In the motion pictures of the crash illustrating this effect, look for a continuing series of flames at the engine exhaust following crash impact at the barrier. As the airplane skids along the ground, the fuel spilling from the wing at this location moves span-wise in mist form until it reaches an exhaust flame just before the airplane stops. Now let us observe this method of fuel movement to the engine tailpipe. The action here is reduced to 1/5 normal speed. Notice the flames at the tailpipe. Contact of the fuel mist with an exhaust flame occurs just as the airplane comes to a stop. Ignition of the fuel mist occurred on the same airplane on the hot exhaust collector ring of the engine on your left at this location. Under impact at the barrier, the engine nacelle breaks down and exposes the exhaust collector ring. As the airplane slows, the fuel mist moves span-wise and forward to the exposed collector ring. Here comes the same airplane. Watch how the nacelle on your left tips downward as the propeller hits the barrier, exposing the exhaust collector ring. The flame first appears at the top of the nacelle where the fuel mist contacts the exhaust collector ring. In the time between initial fuel spillage and ignition, an explosive fuel-air mixture accumulated in the wing. The explosion of the mixture produced this distribution of flaming fuel. Fuels of low volatility in mist form ignite readily in spite of the fact they are safe in liquid form in the presence of open flames. A wick saturated with this fuel can be ignited by the steady application of a flame. The lighted match held above the surface of this low volatility fuel produces no ignition. Observe in the next crash the ignition of the mist of low volatility fuel by a tailpipe flame. Note also the backfire flame at the engine inlet that follows the main fuel ignition. The tanks of the oncoming plane are filled with low volatility fuel. This action is reduced to 1/5 normal speed. Here is the ignition by the tailpipe flame. Now watch for the backfire at the engine inlet. This aerial view of the crash with the action slowed to 1/3 normal speed shows the flames traveling through the fuel mist at a rate comparable to that of gasoline. The flames at the engine exhaust that were observed igniting these mists may occur in a crash as long as the engine is rotating and drawing fuel. Even impact of the propellers with an obstacle does not ensure that the engine will stop running. In this crash, shown at normal speed, the damaged engine continues to operate for several minutes after crash impact. Watch how the propellers, now in slow rotation, accelerate. This alternation of slow and fast rotation continues through several cycles, one of which is shown here. Another ignition source in the engine nacelle which may ignite the fuel mist is provided by lubricating oil burning within the nacelle. The next crash you will see shows how the lubricating oil can set fire to the fuel. On the low-wing airplane used in this crash, the nacelles strike the ground when the landing gear is sheared off. The oil cooler located at the bottom of the nacelle is ripped open when the nacelle strikes the ground. The released oil is ignited on contact with the hot engine exhaust collector ring close by. Now we shall see how this fire-setting process acts in a crash of a low-wing airplane having the nacelle arrangements shown previously. The action is reduced to 1/12 normal speed. After passing through the crash barrier, the unsupported airplane strikes the ground, nacelles foremost, causing the oil cooler in the nacelle to break back and release oil onto the hot exhaust collector ring. Now, condensed oil vapor generated on the exhaust system can be seen issuing from the nacelle. As the airplane slows, the fuel spilling from the wing moves out ahead of the leading edge and spreads toward the nacelle. 2 seconds after crash impact, ignition of the oil is indicated by the fire detectors. A marked increase in the rate of formation of oil vapors follows ignition of the oil. 3 seconds after crash impact, the entire engine exhaust collector ring is enveloped in fire. As the airplane comes to a stop, the fuel mist and oil vapors form a continuous combustible atmosphere. The nacelle oil fire spreading through the oil mist will now appear outside of the nacelle and move rapidly to the fuel. Watch how the fire moves to the breach in the wing and then to the rear of the airplane as it follows the fuel spilled in the slide path of the crashed airplane. Finally, it is necessary to consider the time during which the mist is a hazard. This is a rear view at 1/3 normal speed, which places the fuel mist between the airplane and the camera. The developing fuel mist obscures the airplane from view, but it reappears shortly as the large mist droplets rain to the ground and the small droplets are swept from the area by the wind as they evaporate. These mists seldom remain around the crashed airplane for more than 15 seconds. Analysis of the photographic data shows that this fuel mist hazard time varies inversely with the wind speed around the crashed airplane. To sum up, it has been shown that airborne fuel mist can move considerable distance forward and span-wise from the fuel spillage point to reach remote ignition sources. When the fuel is dispersed as mist, it ignites readily even though its volatility is low. Contact between the mist and an ignition source far from the fuel spillage zones is most likely to occur as the airplane slows down. Because of the short duration time of the mist, the ignition source must be present while the airplane is in motion or shortly after it stops if a fire is to occur. Now let us see how crash fires are started with fuel spillage in liquid form. Fuel in liquid form appears on the outside of the airplane, pouring to the ground from the broken fuel tank and fuel lines. The steam that is issuing from the nacelle will be discussed later. Liquid fuel also collects on the airplane's surfaces by interception of the fuel mist droplets. While the streams of liquid fuel pouring to the ground are formed as the airplane comes to a stop and mist formation subsides, spreading of the liquid fuel within the airplane structure begins as soon as the tanks are damaged, regardless of the state of motion of the airplane. When liquid fuel is spilled inside the airplane structure, such as the wing interior, combustible concentrations of fuel vapor accumulate readily and spread within the structure. As an example of the ignition of fuel spilled within the wing, observe the wing fire set by damaged landing lights on the leading edge of the wing. The poles that rip open the fuel tanks also smash the landing lights and drive them into the wing, where the incandescent filaments set fire to the fuel almost at once. The next motion picture sequence, projected at 1/5 normal speed, shows ignition by the damaged landing lights. The pole at the barrier drives the landing light into the fuel tanks. The resulting fire spreads rapidly through the fuel mist to produce this wall of flame. The mass of fuel mist rises as it burns out. The fuel evaporating from liquid spillage on the ground and the wetted surfaces of the airplane continues the fire on a reduced scale. The fuel that spills in the wing can also move through channels within the wing to ignition sources contained in other parts of the airplane. One path this fuel may take is through the duct in the wing leading edge. This duct carries hot air to warm the wing and prevent the accumulation of ice in flight. The duct leads to a heat exchanger at the engine exhaust tailpipe, which provides the necessary heat. When this duct is ripped open as the poles tear through the wing, some of the fuel issuing from the torn tanks is diverted into the duct. This fuel flows by gravity to the hot heat exchanger. Upon ignition, the flame flashes back through the hot air duct to the fuel in the wing. Here is a crash in which these events occurred. Because the wing slopes gradually toward the nacelle, the fuel flowing through the hot air duct requires 14 seconds to reach the nacelle. Since the action on film is reduced to 1/5 normal speed, about 1 minute will pass before this ignition appears. The steam which is issuing from the nacelle will be discussed shortly. The fire will show first at the engine tailpipe heat exchanger on your right. Note the spread of the fire back to the wing and the wing explosion that results. In addition to the flow of liquid fuel through the internal channels of the airplane, fuel in rivulets and sheets flows by gravity along the underside of inclined airplane surfaces. This will be called wetting conduction. Fuel which spills inside the wing can seep through seams in the wing skin and cling to the undersurface of the wing. This fuel may then flow to other parts of the airplane where ignition sources exist. The resulting fire travels back along the fuel path to the fuel source. The wetting conduction of the fuel along the undersurface of the inclined wing is illustrated by a simple experiment in which fuel issuing from an opening in a tube at the raised end wets and moves along the undersurface to the low end. The normal wing arrangement of airplanes may place the wing tips higher than the wing at the engine nacelles. For these airplanes, the wetting conduction flow is toward the nacelle where ignition sources exist. Sometimes in a crash, the wing inclination is even higher, which increases the fuel movement by wetting conduction. Distribution of fuel by wetting conduction is shown on the underside of this wing of a crashed airplane which did not burn. The fuel dye indicates the path of the fuel. The continuous fuel-wetted path extends from the break in the wing to the nacelle and the engine exhaust pipe. Here is how the wetting conduction flow looks immediately after a crash. The fuel on the underside of the wing clings and flows by gravity along the wingspan, some of the fuel dripping off along the way. Fuel sometimes runs into the wheel well from broken tanks through channels in the wing structure. Here you see how it dripped and ran along various parts of the landing gear actuating system and along the strut toward the wheel. Any marked change in the surface along which wetting conduction of fuel is taking place may interrupt this fuel flow. Here we see how a sharp-edged projection intercepts the wetting conduction fuel flow and prevents further flow along the rod. A slot in the rod provides the same interception of the wetting conduction flow. In cases where wetting conduction or fuel flow through structural channels results in prolonged contact between an igniter and the fuel in liquid form, the use of fuels of low volatility would not materially reduce the likelihood of fire. Where vaporization of the fuel across an air gap is required for the fuel to reach an igniter, low volatility fuel provides a safety advantage. Consider next fuel spilling in the open air that wets the ground along the slide path of the airplane and around the crashed airplane at rest. The pools of liquid fuel close to the nacelles are not large, since most of the spilled fuel flows away from the spillage point. Ignitable fuel vapor from ground spillage is carried in a thin layer close to the ground. The ignition hazard distance, which extends only a few feet from the spillage, decreases with increasing wind velocity. This short hazard distance is illustrated by the ignition of gasoline vapors from pans by a lighted taper approaching from the downwind end. When ignition occurs, the lighted taper lies within 2 inches of the surface of the gasoline contained in the pans. The wind speed is 10 miles an hour. Movement of combustible concentrations of fuel vapors from fuel spilled in the open air to ignition sources above the ground is considered unlikely. However, when the fuel is spilled into wind-protected areas provided by the crashed airplane, heavy ground vegetation, or ground channels, the combustible concentration of fuel vapors may travel a considerable distance. The ignition source must appear close to the ground in order to contact these fuel vapors. Such ignition sources may be droplets of burning oil, hydraulic fluid, or pieces of hot metal broken from the engine exhaust disposal system. Friction sparks generated by the scraping of airplane metals on concrete runways or stony ground provide one type of ignition source which appears close to the ground. These sparks may ignite fuel on the ground. In order to study this type of ignition, a concrete strip was built along the slide path of the crashed airplane. Selected samples of airplane metals were fastened to protruding ends of pneumatic wheel struts salvaged from airplanes crashed in this study. Upon crash, these metal samples bear on the concrete strip with a contact force great enough to produce sparks of sufficient size and temperature to ignite aviation-grade gasoline. Sparks from this portion of a steel propeller blade and this steel wheel strut produced fires. Abraded particles of this portion of an aluminum propeller blade did not produce ignition. In order to ensure an ignitable mixture close to the ground near the sparks, secondary fuel spillage was provided by the spray bar at the nose of the fuselage and these spray nozzles along the side of the fuselage. Ignition will appear at this point on the fuselage where a portion of a steel propeller blade is located. Here we see the airplane sliding along the concrete strip after undergoing the usual crash damage at the barrier. The action is slowed to 1/5 normal speed. The ignition will appear at the bottom of the fuselage. This is the first ignition, and here is the second. Friction sparks obtained from steel in normal steel grinding operations seldom have enough size and temperature to ignite gasoline. But these studies show that friction sparks of sufficient energy for ignition of gasoline can occur under the conditions of high friction loads which exist in some crashes. To summarize, these results show that the ignitable vapor zones arising from liquid spilling in the open air are small except in wind-protected areas. Liquid fuel spilled in the wings moves as liquid and vapor through the structural channels. Widespread distribution of the fuel in liquid form can occur by wetting conduction. In contrast with the fuel mist, which persists for only a few seconds in the crash area, the fuel in liquid form on the ground and the wetted surfaces of the airplane and in the channels of the airplane structure are present for long periods. These are the forms of fuel spillage that are inflamed by ignition sources which appear late in the crash event. The ignition of fuel, pre-mixed with air in combustible proportions, is another way in which a crash fire may begin. Such fuel-air mixtures appear in the engine air induction system comprising the supercharger and engine intake manifold. A rupture of the engine induction system is followed at once by release of the fuel-air mixture contained under pressure by the engine supercharger. Ignition may occur by contact of this released fuel-air mixture with the hot elements of the exhaust disposal system or exposed exhaust pipes, by arcs and sparks of the electrical system, or by backfire from the engine cylinder. Because of the high airflow rates through the engine nacelle in the early phases of a crash when the airplane is moving at high speed, ignition of this released fuel-air mixture must occur shortly after engine induction system failure. Otherwise, the fuel-air mixture is quickly swept from the nacelle by the airflow. Although the fire produced by the ignition of the engine induction system fuel is not serious in itself because of the small amount of fuel involved, this fire can extend to other fuel being spilled and so set off the major fire. In the next crash to be shown, the engine on your right breaks out of its nacelle at the moment of impact. The engine fractures along a line passing through the case of the supercharger. The released fuel-air mixture is ignited at once by exhaust flame issuing from the adjacent broken engine exhaust. Here the airplane approaches the crash barrier. The action is shown at 1/12 normal speed. Watch the engine in full view snap from its mounts. Ignition of the fuel-air mixture occurs at once. The fuel being spilled adjacent to the nacelle is then ignited from this flash fire. Another crash fire involving ignition of the engine induction system fuel occurred in the following sequence. Damage to the engine induction system on crash impact resulted in a fire at the nacelle in a manner similar to that shown in the previous crash. Fuel spilling from the broken main fuel line at the nacelle firewall was ignited by the flash fire of the engine induction system fuel. The resulting flames streamed rearward over the nacelle and wing. Afterwards, the fuel spilling from the wings through the ruptures cut by the poles at the crash barrier fanned out into the wake of the wing. Contact between the flames and the fuel took place to the rear of the trailing edge of the wing. The flames moved forward to the wing through the trailing fuel as the airplane speed fell below the flame propagation speed. Now watch this fire-setting mechanism in the next movie sequence at normal speed. Watch the nacelle and note the forward movement of the flame. The research up to this point resulted in an understanding of the ignition sources involved in a series of crash fires and also how the fuel in the mist, liquid, and vapor forms moved from the spillage point to the ignition sources. However, these ignition sources revealed so far usually produced fires within a few seconds after crash impact. Because it was felt these early fires might mask other ways in which fire can occur, the known ignition sources were inerted by experimental means. The parts of the inerting system used in this investigation are shown diagrammatically on this chart. Here are the main parts of a typical engine nacelle. To prevent the appearance of flames at the engine inlet and exhaust outlet, fuel system shutoff valves are installed at the engine and the firewall to stop the fuel flow following crash impact. One valve stops the fuel flow to the engine, the other prevents the fuel spillage into the nacelle. several pounds of suitable fire extinguishing agent discharged uniformly in the engine inlet air to inert the contents of the engine during the period of time required for the valves to stop the fuel flow. An electrical system switch shuts down the airplane battery and generator circuits. The ignition system continues to function so that fuel passing into the engine will be burned in the normal manner in case the fuel shutoff valves and the fire extinguishing agent system at the engine inlet are slow to function. Normal engine exhaust is less likely to start a fire than tailpipe flame, which forms that when the fuel charge passes through the engine cylinder unburned and is later ignited in the hot exhaust system. In order to prevent ignition on the hot metal of the exhaust system, a water spray is used to cool all of the exposed metal, which is hot enough to ignite the combustibles. In the few seconds needed to cool the metal to safe temperatures, an inert atmosphere of steam generated by the water evaporating from the metal itself shrouds this potential ignition source to render it impotent. The portion of the water spray system which services the exhaust collector ring is this 3/4 inch diameter tubing, bent to conform approximately to the shape of the collector ring. The exhaust system receives water over its entire surface from its spray nozzles. The effectiveness of the water spray in preventing ignition on the hot exhaust is demonstrated by the rapidity with which a continuously fed oil fire burning from the exhaust system is extinguished by the water spray. Notice how the application of the water spray extinguishes the fire almost at once. This crash is typical of the results obtained with 5 aircraft equipped with the experimental inerting system just described, which is arranged to be actuated as soon as possible after a crash impact at the barrier. The only visible sign of the functioning of the inerting system is the steam evaporating from the hot exhaust system. This is the steam which was visible in some of the preceding pictures. The fuel here has been dyed red. See the dust being raised by the airplane fuselage skidding along the ground. This dust plays an important part in starting fires to be described shortly. This experimental inerting system used in this crash was devised solely for studies of this kind and does not incorporate the considerations of weight and bulk which would be involved in inerting equipment for operating aircraft. In this phase of the research, in which aircraft carrying the experimental inerting system were subjected to moderate damage upon crash impact, no new ignition sources were revealed. After 5 crashes in which no fires were obtained and no new ignition sources were observed, the crash circumstances were modified in an effort to learn other ways in which fires may occur. In order to learn whether ignition sources may be created by the tearing and twisting of the airplane structure in a severe crash, the forward portion of the fuselage structure was crushed along this inclined line in one crash. As before, the nacelles carried the experimental inerting system. In the pictures which follow, note the complete collapse of this fuselage forestructure, bringing the wings to ground level and the resulting wetting of this structure by the released fuel. While no fire occurred around the crushed structure, ignition of the fuel did occur in the fuel-wetted wake of the airplane. The ignition source was an electric spark discharging to the ground from the landing gear strut, which broke off in the crash and tumbled in the wake of the airplane. Here the airplane approaches the crash barrier. Upon impact with the ground, the forward structure collapses. The action here is slowed to 1/5 normal speed. Now watch the wheel strut tumbling in the wake of the airplane and observe the ignition which occurs when the metal end of the strut approaches the ground. The fire spreads through the fuel in the airplane wake. There is no evidence of other ignition resulting from the destruction of the fuselage structure or the inerted engine nacelles. The igniter in this instance proved to be an electric spark discharging from the landing gear strut to the ground. The necessary electrical potential on the strut was generated in its passage through the dust and fuel mist in the wake of the crashed airplane. Ground studies were conducted by blowing dust and fuel over a landing gear strut and measuring the electrical potential built up on the surface of the landing gear. Here is the landing gear strut, electrically insulated from its supports. When dust is introduced into the air, blowing over the strut at speeds equal to that of the strut moving through the air in the crash, potentials in excess of 20,000 volts are generated on the strut almost at once. This voltage applied across a spark gap located in this small pan containing a pool of gasoline produces ignition of the gasoline. Here is the flaming gasoline. In the last crash of this series, the effect of an airplane ground loop on the distribution of the spilled fuel was studied. Watch how the airplane ground loops as one landing gear is torn away. The ground loop places the airplane in the fuel spray. The fuselage, wing, and nacelle on the right side of the airplane are wetted heavily with fuel. Because the inerting system carried on this airplane functioned properly and no new ignition sources appeared, no fires occurred. And now, here a summary of the crash fire research from two Lewis Flight Propulsion Laboratory scientists, Irving Pinkel, Associate Chief of the Physics Division, and Merritt Preston, Chief of the Flight Research Branch. Mr. Pinkel.
The results of this work indicate that significant reduction in crash fire hazard can be realized by design measures that increase the spanwise and forward distance and the elevation of the engines with respect to the fuel storage. This trend in airplane component arrangement decreases the likelihood of contact between the fuel mist and the many ignition sources located at the engine nacelle. Fuel stored in wingtip tanks or in pods suspended below the wing represent current design trends which decrease the likelihood of contact between the fuel and the ignition sources. Devices or design features which act to intercept spilled fuel flowing within the airplane structure are also valuable. Provisions for the drainage of this intercepted fuel into the open air at spillage points away from the engine nacelles would enhance the effectiveness of these arrangements. The location of landing lights away from chordwise positions in front of the fuel storage is indicated as well. Because these studies show how readily combustibles spilled in the nacelle are ignited, it is desirable that the components of the fuel, lubricating, and hydraulic systems should be located high in the nacelle where crash damage to these components is least likely. Tubing containing combustibles should be designed to accommodate the nacelle distortions accompanying propeller and nacelle impact. Preliminary data suggest the value of employing special paints which reduce the tendency toward the formation of electrostatic sparks on parts of the airplane likely to be detached in the crash and trail in the dust and fuel in the wake of the crashed airplane.
In an approach to an indicated crash landing, the pilot should de-energize all of the electrical system not required for the landing. Engine operation that provides the coolest exhaust disposal system should be practiced consistent with other safety considerations. Just before touchdown, the fuel flow to the engine should be cut off to allow the engine to be purged with clean air. In view of the effectiveness of the experimental ignition source inerting system in preventing crash fires experienced in this research, further study of this system for special airplane application is desirable.
The material covered in this motion picture has been published in an NACA research memorandum entitled Mechanism of Start and Development of Aircraft Crash Fires.
A detailed description of the method of conducting these crashes was published in the NACA research memorandum entitled Facilities and Methods Used in Full-Scale Airplane Crash Fire Investigation. To understand how crash fires begin, it is necessary to learn where and when ignition sources exist and how the combustibles move from the spillage zones to the ignition sources while these sources are still potent. Many ignition sources are carried on the airplane, others are generated in the crash area. A large number of ignition sources are located in the engine nacelle, which contains the engine and hot metal parts of the exhaust system. Flames appear at the engine intake in the familiar backfire. Likewise, flames appear at the exhaust outlet. The electrical system of the airplane represents the most widely distributed. Off accident was chosen for study because the chance for passenger survival of crash impact is highest in this type of crash, which occurs at reduced airplane speed. The airplanes were carefully instrumented to collect detailed information during the crash. 72 vapor detectors located in the engine nacelle, wings, and fuselage registered the presence of combustible vapors. Over 100 flame detectors, similarly located, recorded the origin and spread of fire throughout the aircraft structure. All the main electrical circuits were monitored at the locations shown on this chart to indicate the presence of short circuits. Instrumentation was also provided to indicate the time at which fuel lines ruptured in a crash. Such detailed information is registered on this instrument panel inside a fireproof box carried in the airplane. The instrument panel is photographed by motion picture cameras. As part of a continuing program on aviation safety, the Lewis Flight Propulsion Laboratory of the National Advisory Committee for Aeronautics has been engaged in research on the start of fires that sometimes follow airplane crashes. The work was undertaken at the recommendation of the NACA Committee on Operating Problems and the Subcommittee on Aircraft Fire Prevention. These groups are made up of leading representatives of civil and military aviation. It was the purpose of this research to provide a better understanding of the important factors involved in the start and spread of crash fires as a necessary first step leading to significant reduction in the crash fire hazard. The work reported in this film covers only the research completed on airplanes powered with reciprocating engines. A thorough review of civil and military crash fire records emphasized the need for well-defined information on how crash fires start. This review showed this information can only be provided by full-scale crash studies. Findings of this study were published in an NACA research memorandum entitled Analysis of Multi-Engine Transport Airplane Fire Records. With the need for a full-scale crash fire program established, the United States Air Force provided a group of service-weary aircraft marked for decommission with which to conduct the research. A landing or takeoff within the box. In a crash operation, the airplane is accelerated from rest under full power and is guided into a crash barrier by a slipper in sliding contact with a rail. This barrier is composed of an abutment in the path of each landing gear wheel. The abutments strip the landing gear from the airplane. The propellers strike the abutment at full engine power to produce extensive damage to the engine nacelle. The pair of poles on each side of the abutment cut into the wing fuel tanks, causing spillage of the fuel. At the moment of crash impact, the airplane is moving at about 90 miles an hour. The airplane carries 1,000 gallons of fuel in the tanks outboard of the nacelles. The fuel is sometimes dyed red for photographic purposes.